All right, so let's get started. So today we will focus today, tomorrow, in that uh, in the next couple of lectures, we will focus on data representation, data types, and uh, conversion from data of one type to another type, so on and so forth. So this forms the foundation for the programs that we write. We have seen these ideas before, but I want to review these ideas one more time and see uh, that these foundations are properly laid out. So if you take any program, as you know, so there are two important parts in a program. Uh, so a program consists of data and computations on data, right? So for example, if you take any C function that we write, like let's say if you have something like main, so to start with, you declare the variables that you would like to use, the scalar variables that you like to use, the arrays that we would like to use. So initially here at the beginning, you kind of declare variable declarations, declare how you are going to store your data and what is the data type, so on and so forth. At the beginning of main, you do it. Followed by that, you have code. This code corresponds to the computations. So not only main, if any function, if you think, so if you take any function, so you pass this function takes some parameters, and so this function takes some parameters. So you have these parameters, and then it also has some return type. And then again at the beginning of the function, you have data declarations or variable declarations. And then you have a bunch of code which works on this, which acts on this data. All right. So given any programming problem, the first thing that you need to understand is what is the data involved in that program and how you would like to represent that data. Do you want to store that data in an integer variable or a floating point variable or a character, or you want to use an array of characters or an array of integers, or do you require a structure or you require a union? Uh, so the first problem that you would like to you have to figure out is, given a problem, how is the data stored? How do you like to organize the data? Number one. Number two is no, and then you yeah the next part is, of course, in order to process that data, you need to come up with some algorithm, a sequence of computations which act on the data. So if you look at the bare bones computer, so if you go in the next semester, you will study computer systems organization course. From the processor perspective, every computing system. So just want to recap again. I want all of you to really pay attention, so that if any one of you are missing out on fundamentals, you can kind of get them back again now. So you have your processor and then you have your memory. Your memory is a linear array of bytes. This is your memory. This is your, we call it as main memory or random access memory. So this is a linear array of bytes, and every byte is 8 bits. Okay, so every byte, so you store 0 1 0 0 1 1 1 1 0, something like that. I hope there are 8 bits here. Okay, yeah. And then this is 0th byte, first byte, second byte. So every byte has an address. So every your memory is a linear array of bytes, and your CPU, the program and the data on which uh, your processor should be working upon, it is stored in the memory. And then, of course, you have your secondary storage structures like SSD, HDDs, which kind of interface with your memory. So your program is present here, your a.out, you give your program for execution dot slash a.out, and your program and data will be loaded to the memory and the processor will execute your program. This is your baseline. So if you go look at your memory, so your memory is a linear sequence of bytes and every byte is a sequence of 8 bits. So if I ask you what is present at a location, at the memory location 2, okay, so let's say we don't have access to the source program or anything. Pose a question. So hey, can you tell me what is present at memory location 2? Will you be able to tell that? Will you be able to say what is present at the memory location 2? So Balaram says it's not possible. Why? Maybe the kernel, okay. Garbage value. The data might not be completely stored in single byte. Excellent point, Balaram. Any more answers? RAM has BIOS, kernel, heap, stack, so anything is possible. Good point, Sanyam. So you all have very many interesting answers. So first of all, you don't know what is present in this section of memory. And even if you know, let's say, your program data is present in this section of memory. So by looking at the bit pattern here, by looking at the 8 bits present here, we will not be able to say whether it is representing a character or that byte is part of a sequence of, like for example, there are multiple possibilities here. So the memory location, let me use mem of 2, indicating that at the memory location, at the location 2, at the byte number 2 of memory, there are multiple possibilities. Like for example, one possibility is you are storing a as character there. You could be storing a character there, or it could be possible that you are storing a byte-sized value. It's not a character; it is some kind of integer you are working with. No, but the size of that integer is restricted to 1 byte. That means it fits into 1 byte. Or it could be the case that no so actually from mem2 to 2 3 4 5, an integer is stored. Like for example, in C, an integer is allocated 4 bytes of memory. So an integer could be present starting from the at the memory locations 2 3 4 5. uh, so Yeah, that is a possibility. So this, at the memory locations 2, 3, 4, 5, there could be an integer present, and there could be an unsigned integer present. There could be a float present, so on and so forth, right? So just by looking at that data, that bit pattern, we don't know anything. Okay, we'll not be able to say. A bit pattern by itself doesn't tell you what it is. It is the semantics that we give to the bit pattern, no, that gives significance to that bit pattern. Are you with me here? If I just show 8 bytes on my line, no, you are looking at my face on this webcam through this. If on my face I wrote 8 bits, okay, you will all be able to see those 8 bits. And if I ask you what does those 8 bits represent, those 8 bits could be, no, like for example, my birthday, uh, or they may represent my age, or they may represent my height, or they may represent anything. So bits by themselves doesn't have any meaning. It's the semantics that we give to the bits that matters. That matters. Are you with me here? So in order to illustrate this particular point, like some of you would have wondered, in one of the previous classes, we have written a program where we do something like %d, %c, and there is a character variable c, we print it twice. And maybe before the printf statement, we may have something like c is equal to small e or something like that. We may have a statement like this. Then what happens is, uh, this assignment statement, the ASCII value of small letter a is 97. So 97 gets encoded as a sequence of 8 bits, and it gets stored in C, and C is allocated 1 byte of memory. So C is right now holding, let's say, 97, the decimal value 97, or the binary. But in the memory, we cannot store 97. The binary equivalent of 97 will be stored in the memory. The binary, the binary equivalent of 97 will be stored in the memory. The same bit pattern you can take and you can interpret it as an integer. So when you tell printf to print 97 and give %d, printf interprets that 8-bit pattern as a integer and prints it as an integer on the screen. So it prints 97. But we tell printf to interpret the same 97 as an ASCII character, then it will print A on the screen. So the same bit pattern, when interpreted as just a value, an integer value, integral value, it is equal to 97. But if it is interpreted as a character, it becomes A. And this is so in one of the classes we have written this simple code in order to print characters from something like we have written C is equal to A, C less than or equal to. Do you recall this code? Did we write this code, guys? And then we have this printf statement here. The same printf statement that we have, this printf statement. So the same printf statement is present here. So here what is happening is the ASCII value in this for loop, the ASCII value associated with A is which is 97 is assigned to C. In the memory location associated with C, the equivalent 8-bit pattern, 8-bit binary number will be written, and you print it using this printf statement, and then you at the end of the for loop you increment C plus C. So the integer value 97, when we do plus C, what happens is this operator just thinks of it as an integer and just does a regular integer increment. And then here you compare it, C with the ASCII value associated with Z. If it is less than Z, you go ahead and again do the printf statement. The point I want you to understand here is there is an 8-bit pattern, 8-bit binary number. That 8-bit binary number, we are interpreting it in two ways. One is as a character and other is as an integer. Because of this, because otherwise if you see uh, uh, from English language perspective, what does incrementing a character a means? It doesn't have any meaning, right? From math perspective, from English language or math perspective, in mathematics there is nothing like incrementing a character a or comparing one character with another character. So all those things are not there. But then we kind of conveniently interpret it as either as a character or as an integer, depending upon what logic we have in our mind. Are you all with me here? Yes or no? Are you able to hear me? Now what I'm telling is, so there is a, in the memory there is, let's think of the character C is allocated memory, this particular, this memory location is associated with character C. The point that I am trying to make is 00101001. Okay, there is a binary number there, and that binary number we can interpret it as a character or as an integer. So when we say plus plus C, this binary number, we are treating it as a integer, as an integer. And but when we see, when we are comparing it, but let's say when we are printing it on the screen, we can, and using this %C format specifier, that binary number is interpreted as a character, and the corresponding ASCII character will be printed. So what we are trying to do is the same binary representation. We are kind of working in two worlds. Okay, so there is some binary representation. So one world is the world of characters. So this could mean C or whatever. And if you go this way, it represents 1, 2, 4, 8, 16, 32, 41 or something like that. So, so there are three domains in which we are living in. So this is the domain which we are comfortable with, decimal numbers. This is the domain, no? So this is the domain in which human beings we are comfortable with. This is the domain in which computers are comfortable. Okay, your computers are comfortable, and no, this is the domain of characters. Okay, again, no, human beings are fine with the characters. So what we are trying to do is, so the internal representation is this in the within the computer, and when we want to do some arithmetic, so this is we are also happy with characters, but actually, when we are working with characters, this is what we want. But let's say, so this is program wise program. So programs are happy with this. I'm using this notation to indicate this is a program. Programs are happy doing arithmetic on integers. So when we want to work on we want to work on characters, but what we, and these characters, they have some ASCII encoding, integer encoding. Okay, so from here, actually what is happening here is we are moving to this world. We are moving to this world. Let me, yeah. So a character has an ASCII code, but this ASCII code is represented in a binary form, because computers can only store binary numbers. So what happens is when we want to do some manipulation on characters, you do manipulation on no in this space. You do manipulation on this space. Finally, when we want to display something to the user, so you come back to the space which the user is happy with and display it on the screen. Okay. I hope you're all with me. Just want to check. Great. So now let's do one thing. Yeah. So let me look at if you look at the C programming language. So any program, as I said, data plus computations on data. Okay. Just want to write it again here because it's so important. Data plus computations on data. So this is what we need to keep in mind all the time. So if you look at data, so you want to figure out, you are writing a program, like for example, you want to find the roots of a polynomial using Newton-Raphson method. So again, how do you represent the polynomial? In order to represent the polynomial, you have to represent the coefficients of the polynomial. And in order to represent the coefficients of the polynomial, whether you should be using an integer data type or floating point data type or long double data type or double data type, all these questions come up. Or let's say you want to store the student database. A student database can involve the name of a student, roll number, his marks, etc. So what data type to use to store a student record? Okay, so you have learned in one of the previous classes that you can use structures to store a student record. But a structure is not a primitive data type. It is composed of a number of fields, and each field has a data type, right? So when we are working with in any programming language, okay, so when you are learning a new programming language, you need to look for what are the primitive data types provided by the programming language. So first is no, the data types which help you in dealing with numeric data, So in the numeric data, so the first class is integers. Okay. And when we think of integers, there are signed integers and unsigned integers. Like your roll number, you can think of your roll number as an integer, but it's always unsigned integer. Or even your marks, there are no negative marks. The marks go from 0 to 100, so it's a unsigned integer. And then there are different integers of different sizes. Like for example, there is a long integer, and if you don't specify anything, let's call it as default integer, and then there's a short integer. Similarly, you have a long unsigned, default unsigned, and a short unsigned. Okay. And then when we go to floating point numbers, float, you can see that floating types broadly. So there is a default float type, and then there is a double, and then there is long double. And then you have char. Okay. And then you have in C99, there is a new primitive data type which is called as bool _bool. But this will appear as bool by including std lib.h. So in the next class, I will tell you what there is something in order to create new data types. So these are the primitive data types, and so you can see So these two are numeric. In order, when you are working with numeric data, you want to work with integers or floating point data types. And then of course characters are there, and from characters we can compose strings, so on and so forth. But this is the primitive data types that are available. And uh, in the programs that some of your friends have written and which we discussed in the class, you would have seen this bool data type. In the next class, we will see a statement called as a typedef statement. Using the typedef statement, it is possible for us to create new data types. So like for example, we can say typedef underscore underscore bool. Some statement like this would be there in not stdlib, stdbool.h. So when we want to use this bool data type, this particular one, you have to include stdbool.h, because stdbool.h, it creates this new data type by using this typedef statement. All right. I am not sure exactly the format of typedef. Maybe, yeah, I think this should be all right here. Are you with me here on the typedef? Or like for example, you can also have a typedef. You may have noticed size underscore t data type. So unsigned int size underscore t. So size underscore t is a new data type that is defined from the basic data type, primitive data type. So in your program, once you define this in your program, when you say size underscore t, no, some roll number, then that means it's your roll number is of type unsigned int. Are you with me? Do you understand this typedef statement? The point here is you have the primitive data types, integers, floating point data types, character, bool. From these primitive data types, we can construct new data types. Like for example, you can have an array of integers, or you can have a structure which is composed of these, which is an aggregate of fields which are coming from this primitive data type. You can have a union, you can have an array of structures, you can have a structure which contains an array. And so from this, programming languages provide these primitive data types and a methodology for us to compose new data types from the primitive data types. So the important point is, let me summarize here, all programming languages, they support two things. So one is primitive data types. I'm using PDT plus primitive data type plus a mechanism to create or compose new data types. Okay. So this is very, very important. So are you all with me here so far in today's lecture? Siddiq has a question. I will take that question, but generally want to get a feel that if you're all with me or not so far in today's lecture. I'm repeating these ideas because there are some students who are struggling. I want all of you know to in the next 2-3 weeks, let's try to make a very good effort to strengthen our foundations. Because no, writing more complex programs, it just comes with experience. Okay, it's nothing to worry. But these foundations, it should be there. If you don't have these foundations, it becomes a struggle. All right. And each of these data types, so they will be allocated memory, like for example, integers, the long integer may be allocated 8 bytes of memory, and default integer, so in many machines this could be allocated 4 bytes, and short integer it may be allocated 4 bytes of memory. And the same, even unsigned or signed, it would be the same. So type def, so the question is, there are, yeah, so two questions. One is Siddiq's question, that can we create a numeric data type of larger memory? It is difficult, Siddiq. It's not easy to create. It's not, I don't say difficult or easy. So let's say, very nice question. So if you kind of look at the integers, so you have, yeah, let me take a program. Let's do this stop share. I'll answer Parshwa's question also on type def. So let me share screen. You are able to see him at the screen, right? I'll take Siddiq's question and I'll take Parshwa's question. Both are nice questions. Do you see a change in my screen? Just want to double check one more time. Okay. I want you to see how the memory for different variables are allocated. How much memory? Great. So now let's compile this program, new terminal. So I'll just compile this here itself, gcc types.c. Uh, oh, size of int, size of unsigned. Are you all good now? Yeah, I think the whole code is now visible. So Okay. Yeah. So now you can see on the screen the size of short int, either unsigned or signed. When you don't put signed, know that it's by default it is a signed integer. So 2 bytes are allocated for if it's a short integer, and 4 bytes are allocated if it's an integer, and 8 bytes are allocated if it's a long integer. Right? Are you with me here on this one? Similarly, if it is float, float variable is allocated 4 bytes, double is allocated 8 bytes, and long double is allocated 16 bytes. So in the memory, when the address, let's say, if you are working with a, yeah, when in the memory, if you are working, this is your memory. If you are working with a short integer, and when we say the address of that short integer is 4, then that means the whole short integer is represented using 16 bits. Okay, so B0 to B15. 16 bits are used to represent that short integer. You are working with short integer. And this whole thing in terms of bytes, we can kind of look at it as 2 bytes. One is byte 0 and byte 1. So byte 0 will be stored here and byte 1 will be stored here. Does this make sense? Again, want to check you are all with me here, right? So a short integer, it requires 16 bits, and 16 bits, no, there is, in our memory, our memory is a linear array of bytes. This 16 bits, which is 2 bytes, has to be linearized. So when it gets linearized, this byte B0, the lower order byte, goes to this memory location 4, and the higher order byte B1, it goes to memory location 5. Good. Are you all with me here in this particular question? Okay. So Siddiq has this question. Clear all my drawings. So there is control N. Let's try to work on short integers. So let's say I have a short int n1, n2, and one more n3. There are 3 variables, and so you can have n3 is equal to n1 plus n2, and maybe, let's say n1 is equal to some 123 and n2 is equal to some 321, and you can add them up and then you can print them. So when you are working with these primitive data types, the basic operators on these primitive data types, they are already defined. What are the basic operators? Like addition, subtraction, division, computing remainder, and few other operators are already given for us by the programming language. So there are some operators which are already given to us by the programming language. But let's say if you want to compute square root, or you want to of a number, or then that's not a that operator is not available. That operator is not available by default. So there are two options. One option is you may want to check, is there any library provided by the C programming language which contains that operation. Like for example, square root, it could be present in the math.h library. In the math library, the square root function could be present. But maybe there could be, you are trying to do something uh, which your math library also doesn't contain. Like for example, the thing that you want to do is you want to check whether a number is prime or not. Your math library doesn't contain the primality checking function, which takes as an input a number and tells us whether it is prime or not. Your math library doesn't contain. So you have to write it. So far, so good. Doing all right till this point. So now coming back to Siddiq's question that yeah, so I instead of if it is if the integer that you are working with can be kept, can be represented using 16 bits, it is great. You can use shortint. Let's say if it can be represented within 32 bits, 4 bytes, we can use the regular integer. Or let's say if it can be represented using 64 bits, then you can use the long integer. And on the operators on short int, long int, and all those things are available by default. You don't need to do anything. You don't need to do anything special. Like for example, you can just have int. So I can use ses for here as a short, and then so the interesting thing here is, like the addition operation, the operation that needs to be applied on short integers is different from the long integers versus the default integers, because their widths are different. And this is especially more important when we are working with float, double, and long double, because the way we perform arithmetic on double, long double, and float is very different. Like for example, if you have one more thing like a float fn1, fn2, fn3, and then if you have something like fn3 is equal to fn1 plus fn2. So the addition operation, the addition, the algorithm for adding two floating point numbers is very different from the algorithm to add two two integers. But when we write programs, we don't need to worry about all these things, because these are primitive data types, and the compiler automatically uh, takes care of these things in a transparent manner. So we don't need to worry about it. Compiler takes care of this stuff. But let's say the number that we are working with, we cannot be held in 64 bits. We may require 128 bits, or we may require 256 bits, or we may require 512 bits, or we may require 1024 bits. Then there are no primitive data types in C which support integers of that length, which supports integers of that length. So what do we do? And do you really think in practice we need to work with integers of size 1024 bits? Is it necessary? Do you think it is necessary for us to work on in practice to work on integers which require 1024 bits or 512 bits? So Siddiq says we may need it to solve problems in combinatorics. Yeah, maybe. The most common use is when you are working with cryptography. Okay, so the encryption and decryption algorithms, or many encryption and decryption algorithms in cryptography, they involve computations on numbers, large numbers like 512 bits and 1024 bits, etc. In cryptography. Okay, cryptography is a very important field. Like for in when you use SSH, when you use SSL, no secure socket layer communication, and so you will learn later maybe in some course on cryptography, like public key cryptography, private key cryptography, things like that, elliptic key cryptography, digital signatures, etc., you will see that we will be working with numbers of really large size. So when we are working with numbers of large size, like for example, if you want to have, like the length of, so the length of unsigned long, uh, yeah, so let's say unsigned long int, yeah, so key 8. So using unsigned long int key, this particular variable, so the size of each element in this key array, it is 8 bytes. So 8 bytes is 64 bits. And so by declaring an array of 8 such elements, so we will be able to store in the memory, no, so 8 times 64. How much is 8 times 64, guys? 512. Yeah, 512 bits. Let's say if you are working with 512 bit numbers, then this could be 512 bit. But the problem is, let's say you cannot, you have two things unsigned in key 2, and so you cannot say key 3 is equal to key 1 plus key 2. It doesn't make sense because it's these are not primitive data types. So your compiler will not be able to compute the sum even before we get there. So your 512 bit number, what do you do is you have your 512 bit number. So your 512 bit number, it is an array of 64 bytes. Okay, so this is byte 0, this is byte 63, and the first byte B0, so the first 7 bytes, okay, that is B0 to B7, B0 to B7, they could be present in, they correspond to key 1 of 0. The next 8 bytes, they correspond to key 1 of 1. The next 8 bytes, they correspond to key 2 of 2, so on and so forth. And in terms of main memory, the whole thing, this whole array key1 is kind of laid out like this. So number one, first, this is, if you want to see it this way, this is B0 to B7, and this whole thing corresponds to key 1 of 0, and then after that B8 to B15, will be there, and these things they correspond to uh, key 1 of 1, so on and so forth. So now the addition on these 512-bit numbers is not given to you. You have to write your own routines. Like for example, you may want to write a routine such as no, void no, add 512 uh, unsigned long, and then you this in this function uh, yeah, so you write code which takes two integers which are two unsigned long int arrays, and adds them and stores it in a third unsigned long int array. But we are using this unsigned long int array to store a 512-bit number. So what is the logic to add two unsigned long? So generally without, if you, how do you add two numbers, two bit number, two binary numbers? Like if you have something like 10010 and 101010, how do you add them? 0 plus 0 is 0, 1 plus 1 is 10. So this you get 1. So 1 plus 1 is 10, so on and so forth. You know how to add binaries, right? So yes or no, approximately. Maybe we'll see that also in the next class. But there is a way to add two binary numbers. So what you do is, okay, don't worry. We will talk about how to do a binary arithmetic maybe in the next class. Uh, but the idea is you need to come up with an algorithm to add these two 512-bit numbers. The algorithm for binary addition we will see in the next class. But for the time being, argue with me on this particular idea that when we are working with 512-bit numbers, for example, we need to kind of find a workaround for this and write our own operators, so on and so forth. Argue with me till this point? Does this make sense? Okay. Great. So these are the foundations, and so there is one question on type def from Pravash, I guess. That question I will take in the next class. I will give a much comprehensive answer to your question on type def in the next class. I think maybe I will conclude this lecture here, and yeah, so if you have any questions here, you can ask me. In the next class, we will work with in the next class, we will see type def, we will see binary representation of numbers, and yeah, the previous lecture I will upload the lectures today itself. So there are two questions. Yeah, so if you want to store an array of bits, in very inefficient way to, but still one way to do it is you just declare you know char um, bits, 10. So you use 1 bit to store 8 bits, but it's okay. Yeah, it still works. But there are better ways to do it, but this is one way of doing it. If you are trying to work on the subset problem, you can kind of use this, or or you can use bool set, something like that. The better way is to pack them as an int within an unsigned long int, or use an array of unsigned long ints or array of characters, things like that. I have two good questions, Treyans. Is there any data type of size 1 bit? I have to check. Yeah, good question. I am not sure. I don't think. Let me check. See, we can store a bit in a byte, but no, there is 0 or 1, but it's not efficient. Shreyans, is there a way to, uh, is there any data type for bits? I am not sure. I have to check. Okay.